Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will examine the efficiency of jobs on the Betzy Linux cluster. Before we begin, let's summarize the tests on Betzy that we covered in videos 33 and 34. The table presents the results from these tests on Betzy, alongside the results from tests conducted on Fram. Note that on Betzy, we utilized 128 CPU cores, while on Fram, we used only 32 CPU cores. In video 33, we performed matrix multiplication using the highly optimized routine from the Intel Fortran compiler with matrix dimensions of 32,768 and 65,536, resulting in wall times of about 38.8 and 248 seconds. In video 34, when we applied the MKL routine, the wall times became approximately 30.7 and 197 seconds. We concluded that the highly optimized routine from the Intel Fortran compiler, red arrows, was slower than the MKL routine, blue arrows, on Betzy. To obtain a more accurate measurement of CPU efficiency, we have conducted additional tests not shown in these videos. Initially, we used a job script that only compiled the Fortran program to create the executable, by commenting out the execution part. Subsequently, we performed matrix multiplication by excluding the compilation process. This approach allowed us to obtain a more accurate measurement of CPU efficiency for the parallel computing involved in matrix multiplication. The results from this approach are shown in the table, indicating that CPU efficiency is higher when jobs exclude the compilation process. The MKL routine achieves a shorter wall time compared to the optimized routine provided by the Intel Fortran compiler, suggesting that the MKL routine performs better on Betzy. This is due to the Intel Fortran compiler not being ideally suited for the AMD architecture, and the need to exclude the X-host compiler option when using the MKL routine. Interestingly, while the Intel Fortran compiler's routine shows higher CPU efficiency, the MKL routine still provides superior performance. This highlights that high CPU efficiency doesn't always translate to optimal performance. On Betzy, the MKL routine is more finely tuned and offers the best performance, even with lower CPU efficiency. We will now explore the efficiency of jobs on the Betzy Linux cluster. We will examine jobs scheduled from February 25, 2023 to 10th of August, 2024, covering a period of about 16 months. During this time, 400,000 jobs were scheduled on the Betzy Linux cluster. Jobs with a CPU time of more than 2 hours consumed about 1,241 million CPU hours, with a total of 187,332 such jobs. In contrast, jobs using less than 2 CPU hours consumed about 0.06 million CPU hours, with 212,668 jobs in this category. The figure displays a histogram of the CPU efficiency for jobs that used more than 2 CPU hours, consuming approximately 1,241 million CPU hours in total. The horizontal axis represents CPU efficiency as a percentage. The vertical axis indicates millions of consumed CPU hours. The first column in the histogram shows that jobs with less than 1% CPU efficiency consumed about 36.9 million CPU hours. These jobs requested more than 128 CPU cores, but only utilized one core. They were scheduled as parallel computations, but did not execute in parallel, using only a single core. Consequently, the CPU hours consumed by these jobs were largely wasted. Why does this wastage occur? Requesting more than one CPU core in your job script does not automatically ensure that your job will execute in parallel. There are several additional steps required to ensure that jobs perform parallel computing. In video 33, we demonstrated that many steps are required for parallel computing with OpenMP. First, we requested 128 CPU cores on a single compute node. Next, we set the OpenMP environment variable to control the number of threads, setting it to 128 to match the number of CPU cores per task. We then included the OpenMP option in the compilation command using the Intel Fortran compiler. Finally, we used OpenMP directives within the Fortran program. These steps highlight that at least 4 actions are required for parallel computing with OpenMP. It's crucial to determine whether your software can perform parallel computing and to understand the options you need to specify to enable this beyond just requesting more than one CPU core in your job script. If your software cannot perform parallel computing, you should schedule it as a single core job on the Saga Linux cluster. Doing so will help prevent the waste of CPU hours on the Betzy Linux cluster. If you've made an effort to perform parallel computing but are experiencing low CPU efficiency, you can request extended user support. These projects do not require any funding or in-kind contributions from the project or user. The total work effort should not exceed 70 to 80 hours over a maximum of 2 to 3 weeks. A possible outcome of extended user support is the development of an advanced user support project, which requires an application and evaluation. This could result in a few months of dedicated work from one of our experts. The next significant column in the histogram indicates that jobs with CPU efficiency between 12 and 13% consumed approximately 25.5 million CPU hours. Many of these jobs use an outdated job script from the Stalo Linux cluster, which are designed for 16 CPU cores per node. The Betzy Linux cluster has 128 CPU cores per node, leading to a CPU efficiency of about 12.5% for these jobs. This means roughly 90% of the CPU hours are wasted. It's crucial to recognize that using the same job scripts across different Linux clusters can lead to inefficient use of CPU resources. The next significant column in the histogram shows that jobs with CPU efficiency between 24 and 25% consumed about 48.7 million CPU hours. Most of these jobs use job scripts from the Fram Linux cluster, which are typically designed for 32 CPU cores per node. The Betzy Linux cluster has 128 CPU cores per node, resulting in a CPU efficiency of about 25% for these jobs. This means that about 75% of the CPU hours are wasted. It's crucial to understand that using the same job scripts across different Linux clusters can lead to inefficient use of CPU resources. The next significant column in the histogram indicates that jobs with CPU efficiency between 49 and 50% consumed about 118 million CPU hours. These jobs use only half of the CPU cores, leaving the other half idle. While this can lead to wasted CPU hours, some jobs may benefit from using only every other CPU core on the Betzy Linux cluster. This is because the cache system can become a bottleneck for certain types of jobs. We will discuss this further in our upcoming videos. The tallest column in the histogram is jobs with nearly 100% CPU efficiency. It's important to note that even if your software achieves nearly 100% CPU efficiency in parallel computing, it may not be optimized for the best performance. As shown in videos 5 and 6, making changes to the program and adjusting compilation options can significantly improve performance. The tests highlighted in blue reached nearly 100% CPU efficiency on a single core. Notably, the last test in video 6 performed about 75 times better than the first test in video 5. Thus, optimizing performance on a single CPU core is crucial before scaling up to multiple CPU cores. It is advisable to check if there are optimized routines available for the calculations you intend to perform with parallel computing. If optimized routines are available, such as those in the math kernel library, you should use them rather than creating your own. These libraries, developed by experts, provide significantly better performance than what you could achieve on your own. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder, Cluster, Work, Support, Parallel, Computing, YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos. You can copy any of these files to the home folder. In our next video, we will perform matrix multiplication using the Python programming language. We will also demonstrate how to integrate Python with the Fortran programming language. I am looking forward to the next video, wishing you all happy computing in the meantime.